Hello, this is now question number 4 for AQA AS June 2014 paper. Now, the first question leads me to this. It says, a fluorescent tube is filled with mercury vapour at low pressure. After mercury atoms have been excited, they emit photons. So I've kind of shown it here. I've actually given you a bit of a nod to later questions just in this diagram. So what I've done is, obviously I've drawn a fluorescent tube. We've got the electrons going through and they hit the mercury atoms, give some of their kinetic energy to the mercury atoms. Then the mercury atom, the electron inside the mercury atom, as shown here, goes up and then after a certain period of time falls back down again, emitting a photon with the exact same energy that it's gained. Okay, so and then this coating changes something about the photon and we can now see it. Right, so I've kind of actually given you an answer to quite a few of the questions in that list. So you know, more than welcome to have a stop at it now and have another go at them questions. I've kind of explained the ins and outs of a fluorescent tube. They're the big long things that you see in the long classrooms, unless you're in some kind of weird classroom. Anyway, so first question says, obviously describes this, and it says, in which part of the electromagnetic spectrum are these photons? Well, you've got to remember, obviously we've got a coating, and now that's to change the wavelength or the frequency, because they are related, so the wavelength is 1 over the frequency. So we just say it's the ultraviolet spectrum, so it's basically the wavelengths that you can't see. So that's essentially what it's saying. Okay, and then 4a part 2 says, what is meant by an excited mercury atom? Now, when you look at this exam paper, there's quite a few lines there, but really it's only worth 1 mark, so there's not going to be massive amounts of information. It's going to be one thing that you need to explain. So I've kind of shown it here, but the simple wording that you need is an excited mercury atom. It could be any atom, but in this case it can be mercury. An excited mercury atom is a mercury atom which an electron is moved up to a higher state through gaining some kind of energy. May this be through the electrons, as we see in a fluorescent tube. And the next question is actually just that. It says, how do the mercury atoms in a fluorescent tube become excited? So I kind of explained it at the start. Basically, we have these electrons that are moving through the fluorescent tube. Now, obviously, there's many more mercury atoms than I've drawn there, but it's just to show and obviously they're not to scale, such as the mercury atoms will be a hell of a lot bigger than the electrons. But you know, for my reasoning, the way I've drawn it, these electrons are quite long and thin. Anyway, so basically the electrons are moving because there's a current going through the tube, and they're moving at a given velocity or current, moving flow of electrons. It's going back to like GCSE's kind of crud. And anyway, they bounce into these mercury atoms, and the electron has to give the exact amount of energy, otherwise it wouldn't go up. It can't give half it and go halfway. It's either got to move energy state or it doesn't. So, you know, if it had a bit more than that, it wouldn't move past it. And if it had a bit less than that, then it wouldn't move at all. Okay? So that's essentially what we're dealing with here. Right. So that'll get you, so that'll be answer to 4a part 3. 4a part 4 says, why do the mercury atoms emit photons of characteristic frequencies? Well, there's a couple of things here that we need to relate. This is worth 3 marks, so obviously there's going to be a bit of thinking and writing to do with this one. So to understand this, we need to think, okay, well, it's giving some energy to the electrons in a mercury atom. Now, what are the energies of these photons? How do we calculate the energy of a photon? Well, the energy of a photon, E equals hf, h being Planck's constant, 6.63 times 10 to the minus 34 as a number. So therefore, this h, weirdly in a name, is constant. Planck's constant is constant. So therefore, the only thing that the energy depends on is the frequency. So therefore, when the photon is released, then the only thing that can define its energy is its frequency. Obviously, its wavelength as well, but it's talking about characteristic frequencies. So obviously these electrons are probably likely to all have the same kind of kinetic energy, or thereabouts, and the ones that will have the given energy will move the electrons inside the Mercury atoms up, because the key thing in this is to say what we've mentioned before, is they need a specific amount, an exact amount of energy gained to move up a state, and then obviously the energy to move up a state is released when it's moved down. And as the energy of a photon, we just said, depends on the frequency, because E equals hf and h being a constant, therefore the only thing that, as I said, the only thing that can change the energy is a frequency. And therefore, so you could say each stage has a certain frequency, releases a photon of a certain frequency. So therefore the characteristic frequencies, what that essentially means, they're just trying to be fancy and word it like they're a bit intelligent and mock you, but don't let them mock you, mock them back and say, aha, well I know this, E equals hf, and the specific energy levels to move up, and the energy is released after a certain period of time, which gives a photon of a specific frequency, because the energy of a photon depends on that frequency. Okay, so that'd be your 3 marks there. Okay, so the next question says the wavelength of some of the photons emitted by excitatory Mercury atoms is 254 nanometers. So 254 nanometers. Now nanometers is 10 to the minus 9 of a meter, so it's 254 times 10 to the minus 9 meters, which is 2.54 times 10 to the minus 7 meters. Okay. Alright, so that's essentially what we're looking at here. So anyway, that's just the first bit of the question. So it says calculate the frequency of these photons. Now that is the wavelength. So we have to go back to our good old friend that we learned in GCSE. So the frequency is equal to 1 over lambda, or lambda is equal to 1 over the frequency. Okay, whichever way around you want to think of it. So both mean exactly the same thing, just rearranged versions of each other. Okay, so we need to calculate the frequency of these photons. Right, well, so therefore the lambda is equal to 1 over the frequency, so you just do 1 over 2.54 times 10 to the minus 7 meters. That is equal to the frequency. So if you were to sub that into your calculator, so just check my answers, you would get a wavelength equal to, 3.9 times 10 to the 6 hertz. Okay, so hopefully that makes some kind of sense. The next question says calculate the energy of these photons in electron volts. Well, the first thing we need to do is calculate in joules to be able to convert to electron volts. So we know this is the frequency, we know the energy of a photon, E equals hf, so we just sub in our known values, so therefore E equals 6.63 times 10 to the minus 34 times 3.9 times 10 to the 6 hertz. Remember this is in joules, so E, the energy of that photon emitted, is equal to 2.6 times 10 to the minus 27 joules. Now, how do we convert joules to EV and EV to joules? Right, well, if you think of it, electron volts is the charge of one electron. So the charge of one electron is 1.67 times 10 to the minus 19. Well, that's negative 1.67 times 10 to the minus 19, to be specific. But to think of it as in terms of converting EV to joules, we just leave it as a positive figure. Now, if one electron volt is equal to 1.67 times 10 to the minus 19 joules, then obviously EV is always going to be bigger, because if one EV equals a really small amount of something less than 1 joule, which obviously it is, it's a hell of a lot less, but you just think of it as being less than 1, then EV is always going to be bigger. So if we know the charge of an electron is 1.67 times 10 to the minus 19, then that is, so 1 joule is worth that amount. So therefore we need to see how many joules go into 1.67 times 10 to the minus 19, because 1 electron volt equals that many joules. So hopefully you can see how you think of it. So basically all we do is divide 2.67 times 10 to the minus 7 by 1.67 times 10 to the minus 19. Now you may go, well, surely then that's going to, if that number's on the bottom is surely bigger, don't worry about that. It just, it will come up with the right answer in the end. So that should give you an answer of 1.6 times 10 to the minus 8 EV. Okay, EV, remember, stands for electron volts. Now you could put just 1.67 times 10 to the minus 8 electron volts, or you could leave it as EV. It's perfectly acceptable. Okay, so the next question, 4C, says explain how the coating on the inside of a fluorescent tube emits visible light. So that's this green stuff I've drawn. Now we said obviously that in the ultraviolet spectrum, which means you can't see it. So it's like under a UV light, you can't see it. So this is a very high frequency and a very high extreme wavelength. So if it's an extreme wavelength, obviously we can't see it. So what this coating actually does is, now we have to think, okay, well, E equals HF, so the only thing that can change an energy of a photon, the only thing that can change the frequency of a photon is its energy. So therefore, this coating has to alter the energy somehow of this photon. Now we can't give it any energy because the atoms in this coating aren't moving, it's no kinetic energy, so it can't offer up any energy. So the only thing it can do to change the energy, therefore, is reduce it. So it takes up some of the vibrations, if you can think of it like that. Obviously, I won't put that in your exam, but if it helps you think of it like that, please do. Anyway, it takes away some of the energy of these photons. Now, if it takes away some of the energy, it's going to reduce the frequency, which means it reduces the wavelength, which means we can see it. Well, it changes the wavelength, sorry, so we can see it. So it becomes in our visible spectrum. Okay, so that's essentially how it works. So they're your 2 marks. So 1 mark you need to say it changes the energy of the photons, which therefore changes the wavelength, so we can see it as visible light. So they're your 2 marks. I know it kind of says 3 things, but I think I might have split up the last point into 2, just so you can see where we're coming from. Okay, so that's question 4. Quite a nice question actually. Well, yeah, it's quite a nice paper, this one. I quite like talking about that. So it was just a bit of background on fluorescent tubes. You didn't need to draw that. If you could actually understand what I was drawing then there, I think you deserve an A star anyway, because that's a bit crap. Anyway, so thanks for watching, and we'll see you in question number 5.